Trigonometric substitutions. All right, we've seen two expressions so far. Let's look at our final expression, which is of the form the square root of x squared minus a squared. So to do this, let's evaluate the integral, the square root of x squared minus 25 all over x. So just like in all the others, we say, okay, this looks like an expression involving the form the square root of x squared minus a squared, where a is equal to 5. And this time, when we consider the values that x can be, well, x squared has to be greater than a squared. So that means my values for x either have to be greater than or equal to a, or less than or equal to negative a. So how can we make a substitution that will take care of that? Well, what we can do is consider this function secant theta. The function secant theta takes on every value less than or equal to negative 1 and greater than or equal to 1 exactly once on the interval 0 to pi, as long as theta doesn't equal pi over 2. Since that's the case, we're going to let our x be equal to 5 times secant theta. All right, so now that we've decided to do that, let's go ahead and set up the substitutions we're going to make and our reference triangle. So we said that we're going to let x equal 5 secant theta. That means dx is going to be equal to 5 times the derivative of secant, which is secant theta tangent theta d theta. Solving this equation here for secant theta, we get that secant theta is equal to x over 5. And secant is hypotenuse over adjacent, so our reference triangle will look like this. Here's our hypotenuse over our adjacent. Using the Pythagorean theorem, we get our opposite. And in case we need it, we can also solve for theta by taking secant inverse of both sides of this equation to get secant inverse of x over 5 is equal to theta. All right, so we're ready to solve our integral now. We started out with this integral on the left. We make our substitutions of x equals 5 secant theta here and here. And for dx, we make our substitution of 5 secant theta tangent theta d theta. Now over here, we need to simplify this expression. There's a 5 secant in the denominator and in the numerator. They'll cancel each other out. And here, under the radical, I can rewrite the 5 secant theta squared as 25 secant squared theta. So this integral becomes the integral of the square root of 25 secant squared theta minus 25, all times tangent theta d theta. Now under the radical, I can factor out a 25, and then we're left with 25 times secant squared theta minus 1. Well, secant squared theta minus 1 is equal to tangent squared theta. Making that change here, now we just simplify what's under the radical sign to get, we now want to evaluate the integral of 5 tangent theta d theta. Or in other words, the integral of 5 tangent squared theta d theta. Now hopefully by now you've discovered that if you want to evaluate the integral of tangent squared theta, what you want to do is rewrite tangent squared theta as secant squared theta minus 1. Because once you do that, you know the antiderivative of secant squared theta is tangent theta. The antiderivative of 1 is theta. And we get our answer of 5 times tangent theta minus theta plus c. So now all that's left to do is to rewrite this answer in terms of x. And to do that, we go back to our reference triangle. So let's look at our reference triangle again. I need to find out what tangent of theta is equal to. Well, tangent of theta is opposite over adjacent. So opposite was the square root of x squared minus 25. Adjacent was 5. So we get tangent of theta is equal to the square root of x squared minus 25 over 5. So our answer, we said our integral was equal to 5 tangent theta minus theta plus c. We make our substitutions in. We said that tangent of theta was equal to the square root of x squared minus 25 over 5. We saw that theta was equal to secant inverse of x over 5. And the only thing left to do is distribute this 5 through the parentheses to get our final answer. All right, so we've seen 3 ways to evaluate integrals that involve the square root of x squared plus or minus a squared in some order. So here's how to attack them when you come up to them. First, you want to make the appropriate substitutions. If your integral involves the square root of a squared minus x squared, then you're going to let x be equal to a times sine theta, because that's the one that will make the values of x between negative a and positive a. And then you'll know that dx is equal to a cosine theta d theta. If your integral involves the square root of x squared plus a squared, remember, x can take on any value, so I should make the substitution that x is equal to a times tangent of theta, because that takes on every value. And that means that dx is equal to a secant squared theta d theta. And finally, if my integral involves the square root of x squared minus a squared, then what I should do is I think, okay, my x, the absolute value of my x value has to be greater than or equal to a. How can I do that? That's when x is equal to a secant theta, which then means that dx is equal to a secant theta tangent theta. Once you've made the appropriate substitutions, draw a reference triangle that you can go back to. Evaluate your integral, which now should be in terms of theta. And then when you're all done, use that reference triangle to rewrite your answer in terms of x.